All right, I think I gotta. All right, I think the recording is in progress. So we will go ahead and get started. So thank you for coming to the afternoon session of our Precision Health Bootcamp. Today we'll be talking about high performance computing basics. My name is Dr. Philip Richmond, and we were going to run for about 2 hours, give or take. We'll see how much we get through. Those of you who are just joining us for this session, I highly recommend joining the Slack. I've pasted the slide deck here for today's session. And as we're going to go through this, I'm not going to go into full presenter mode. I recommend you open up the slides, like these 35 people or so here, and have a terminal open as well. So, high performance computing basics. Just like to acknowledge again that we are gathered here on the traditional, ancestral, and unceded territory of the Musqueam people out at UBC. The copyright information for today's session, this is a CC BY SA 4.0, which means you are allowed to share and adapt and transform this content. However, you must provide credit to us, those who created it, as well as the content you create based on this session must inherit the same license. So, some learning outcomes. At the end of this session, you'll be able to use variables within your shell and bash scripts, which execute commands. You'll be able to create a job script header that communicates with the PBS Pro scheduler. And you'll be able to submit your job to the scheduler, check the job status, and examine the output. Let's just make sure. Okay. Good. Hopefully they can hear me online. We'll just go ahead and charge forward anyways. All right. So how to get help during the sessions. You can go ahead and click this code share link, which will bring you to this page. If you like, you can log in there. Anyone can have access to write to this space. And if you have questions, as you can see from our morning questions, we now have afternoon questions. So if there are any afternoon questions, feel free to paste them below there. Okay. For those of us in person, we have a pink sticky note and a red sticky note. If you have the pink one, that's kind of like a raised hand. If you've got the green one, that means good to go. Our TAs online, I think we have Carly and Abisola, and in person we have Jeff and Derek. Where's Derek? Raise your hand. Everybody look at Derek. If you need help, you can ask Derek. He's very good. Okay, as far as the links for today, we have a GitHub gist, but we can also just go to the main Precision Health website here. And if we scroll down, this is the core HPC basics workshop. Some definitions for some things that we're going to talk about. All the commands that we're going to run in this session. You can see it's not nearly as many as the morning session for those of us who are here at 9 a.m. We're going to execute some bash scripts. We'll work with modules, and we'll work with the scheduler. Okay. So a little outline for today. You can see here's Sherlock getting bigger and shaggier. We're going to talk about the motivating data type. We're going to do just a quick touch of the command line. There was a problem set from the morning, although I don't think many people have gotten into it. I will point you to that problem set afterwards if you're interested. Bash scripts, we touched on that just briefly in the morning, and we're going to expand on it. We'll talk about variables. We'll talk about your path, which sounds pretty exciting. Bash scripts with variables, interacting with PBS Pro, and job scripts with variables and conda. This is kind of our final goal for today. So we're going to start with a motivating data type. So my research focuses on rare genetic disease and identifying causal genomic variants underlying rare diseases is important, but also challenging. So it affects rare diseases individually are rare, but collectively they affect about 1 in 12 people. And with as of 2021, you can see that there are over 4,000 rare disease genes that have been implicated to cause single gene disorders. Now, finding the single variant in the entire human genome can be a bit like this guy with his head in the haystack trying to find the needle. And just to kind of show how this even gets more challenging over time, updated from what was this, working on the weekend, Saturday, almost 4,300 new single gene disorders. So with genome sequencing, it used to cost about $100 million to sequence a genome. Now it costs less than 1,000. Thanks to this technology and new technologies that are continuing to come out. Now, we can harness this technology to produce essentially DNA sequencing data that we can then process and analyze to find these rare disease genomic variants. So we're going to do a quick review of how you may go from DNA to candidate variants. Now, this is very brief, and if you're interested in this, I teach other content about it, and I encourage you to reach out. So briefly, what we do is we take some blood, we isolate DNA, we then prepare a sequencing library and run on the Illumina sequencer. And this gives us a set of reads or short fragments of DNA. Now, Illumina short read sequencing, this is not nearly as great as the YouTube videos you can find, and I encourage you to watch those. This is my own version with basic PowerPoint animation. So we have sheared DNA, we prepare a sequencing library, and then it goes into the machine. And on the sequencing machine, our DNA with these adapters, these pink and purple bits, will match to what's called a flow cell. It will undergo a process of bridge amplification to amplify each of those pieces of DNA. And then a sequencing by synthesis reaction happens where the entire flow cell, all of these pieces of DNA, here I'm showing you only 5, but there's hundreds of millions on this little chip that's about that big. We add fluorescently labeled nucleotides, G's, C's, T's, and A's across the entire flow cell. And when one matches to that piece of DNA at each spot, it will bind. We excite it with the fluorophore, and it will release a color. Each of these colors then is done in a number of cycles, where every cycle across the entire flow cell, we are adding 1 base pair to each of our DNA sequencing reads. And at the end, we get out this file, which you may have heard of, a FASTQ file. And we're going to talk a little bit about FASTQ files because we're going to be using them today. So FASTQ files, they represent essentially the raw data format from the DNA sequencing technologies. So there are many different input data types, for example, DNA sequencing, ChIP-seq, RNA-seq, GRO-seq. All of these end up in the same output format, which is why it's useful to touch on this briefly. So the first line. Every read is represented by 4 lines. The first line starts with the @ sign, followed by some information. The next line is going to be the actual sequence of DNA that we have sequenced in that read. Then the plus sign, and then a string of ASCII encoded quality scores. Now, the quality scores that we use in this system show that as the quality score is high, there is a very low probability of error. But as the probability of error increases, the quality score decreases. And when I said ASCII encoded, we have a range of 40 quality scores that we represent with single characters. And so this is one way that we can have more than just 10 different scores represented by a single character. So most DNA sequencing is paired end, meaning that you're going to sequence two ends of the same fragment of DNA. Now, when we map back to the reference genome, you'll know more info about how read 1 and read 2 should map, including their orientation, the fact that we expect them to be facing towards each other, and the rough distance between mappings, which we expect to be normally distributed around the size of DNA that we've prepared, which is about 500 base pairs here. So reference genome mapping to find genomic variants. Essentially, when we've got these DNA sequencing reads, one of the first steps that we can do is we can take them and map or align them against the human reference genome. We can then find places where the DNA sequencing reads do not match the reference genome, and we can then interpret those to find which may be candidate pathogenic variants. And if you were in the morning session, we saw ClinVar. That's a database where we store these pathogenic variants so that we can interpret them when we see them in other patients. Now, in today's session and also with conda and singularity tomorrow, we're going to be focusing on using sockeye to map DNA sequencing reads back to the reference genome. That's the end goal for today. And then tomorrow we will do some variant calling in the morning with the tool called Deep Variant. All right, so a quick review of the command line. This is all we get for a review, and this is really also starting with a setup. So many of you are still new to the command line. Some of you are experts. So we're going to try and aim for a bit of a balance. The commands that I need you to run are going to be shown here in green, and I describe essentially the command in yellow that I need you to replace. For example, here, replace the CWL, which I mentioned with angle brackets, with your actual CWL. So why don't we go ahead, and if you have not already logged in, show you the login. We will SSH your username at sockeye.arc.ubc.ca. We have our lovely two-factor authentication. Okay, so we are logged in. Now, the first command that we're going to run for today is we are going to make essentially a workshop directory in this space: Scratch, TR, Precision Health 1, workshops, student spaces, followed by your CWL. Now, this -p parameter means you can make this directory, but if it already exists, then it will not throw an error. So I can go ahead and copy that. We can go ahead and list out the student spaces to see if anybody has made a directory there. And we can see some people have made a directory. Some people have put some files there that were never cleaned up. Looks like there's a variant summary. No worries. We can handle all of that. So now we're going to change to our workshop directory. I'm going to change to that directory with the cd command. Well, ls. And we've got some things in here. For me, should probably get rid of these. That's the most dangerous command in the book. We're just going to go ahead and run that. All right. Do not run this command. So now we are going to copy a entire directory into this space. And this is going to be called core HPC basics. There's a lot of files in there. All right. Cool. He's going to work for a while on that. All righty. So all right, so we're going to go ahead and copy this directory from project TR Precision Health 1, Precision Health Virtual Environment, Workshops, Core, HPC Basics into this current directory. So I'm going to go ahead and copy that. Now I can change into that directory, Core HPC Basics. And we should see something that says files, problem set, README, scripts, and slides. We'll give everyone just a moment to set that up. Okay. Now, this core HPC basics directory that we copied is going to mirror what you can actually see here on GitHub. So the advantage is that as we explore, for example, the scripts that we're going to be looking at, which are going to be here in scripts, we can look at them both online, like my first job script, as well as on the server. So this will help you as you work on these different scripts. Sometimes it's nice to see it in a different format on the internet. Okay. Yeah, the copy could take a little bit. Okay, so anybody need more time with the copy? Just one? All right. So let's take a moment to look at the organization. So what are you, MOBA Xterm? Sorry? What's your terminal? You can try right instead of using yeah, we've got some TAs, they can sort that out. So let's take a moment to look at organization. So we have a directory for scripts, we've got a directory for files, we've got a directory for problem set, and a directory for slides. And these are the directories here. So in your own projects, consider organization and the file system hierarchy when you're setting up and processing your data, because it will be a lot easier to maintain organization if you have a good plan at the start, as opposed to trying to pull things together after you made a mess of a single folder. So let's go ahead and change into the scripts directory. cd./scripts, and we can ls, and let's go ahead and cat the basic bash script. So again, the cat command is going to print the script to the screen. Go away. Okay. So we printed this script to the screen, and we can see in this script a few different things. So at the top, we're going to see this hashtag followed by an exclamation point /bin/bash. So we call this a shebang, believe it or not, followed by /bin/bash. Now, this is not required at the top of bash scripts, but what this means is that if we were to execute this script, it would use that as the executor. And we can talk about that later. The next thing you'll see are lines that start with the hashtag or the pound sign. Now, those are going to be comments, and these are not things that get executed. So if you need to make a comment, like for example, here I make a comment, the first command, the actual command that doesn't start with the pound sign is the first thing that's going to get executed. So all of these commands, the first we're going to run ls, then make dir-p. Again, we've already made this, so this won't work. We're going to run an echo command. This is the first time you've seen echo. Echo will just print this to the screen. The fourth command is the date. It'll tell us what day it currently is and time. And then we're going to sleep for 30 seconds, which might not be a long enough nap, but we will go ahead and try it. So we can run it, sh basic bash script.sh. And it listed out that directory like we thought it would. It made a directory, but it already existed, so it didn't complain. It told us that Sherlock is a social butterfly, printed out the date, and then it went to sleep for 30 seconds. So you can see it's just what looks like hanging. That's counting up to 30 seconds for this sleep. Now, if we want to stop our nap, we can hit Control-C, and that will kill a job or will kill an operation or command that's currently running. You don't have to, but I think it's cleaner to have. The question was about, do you need quotes around what you echo? And it's not necessary, but I think it makes it clearer what's going to get printed. Yeah. Okay, so now we're going to learn about variables. So variables, there are two types of variables. There are global variables, and then there are variables that we can set. So a global variable is a variable that's going to be the same for all of us on the system. And that variable, one example of that is the $user. So for all of us, this will be set to your whatever your CWL is. So if I do echo $user, it's going to tell me what my CWL is. Now, you'll see why this is valuable to have as we go through this workshop. We can also echo our path. So if we type echo $path, we're going to get out something that looks like this. Now, the path is essentially where the command line will look for the commands that we are typing in and then hitting enter. So, for example, if we were to list out /user/bin, ls/user/bin, we can see there are lots of commands in here that we could run. For example, in the morning, we learned the grep command. You may also recognize the lots of commands. Where's pwd? The pwd command to print the working directory. So if your path doesn't have the directory that houses the command, then you'll not be able to execute it. So if this /user/bin was not in our path and we type pwd, it would say command not found. Now, most Linux and Unix systems will have a /user/local/bin or a /user/bin. So getting familiar with that terminology is useful. But there's also a whole ton of other stuff in our path.
In like the topic, I saw it on the feed. It says like unsupported, and then there's like the comments, and on mine it's invalid. Like where you see the void text goes down.
Oh, this?
Why does it keep saying unsupported?
So that's just a directory. We'll talk about that in a little bit. So this is just a directory where there are other commands. So the user local bin has some commands, user bin has other commands, and every other one of these that's separated by a colon will be a different directory where there are commands. And so some of those are going to be relevant to the module system, which we'll talk about. So if you do module load, we'll get there. You'll see that'll add things into your path.
So long as user is capital first one, it's like when you want to put ls, the user is a automated basis.
So you're wondering why this is all uppercase.
And why is it lowercase? User.
Oh, okay. So this dollar uppercase user, that's a global variable, meaning that's a variable that's going to be set on the system, and it'll always be recognized as capital U, capital S, capital E, capital R. This is not a variable. This is a path on the file system. So this is a directory, actually, right? So it could be uppercase U, lowercase s, uppercase R, right? That's just a directory name. So path and user are two variables that are, they're global. They're always set. Now let's take a look at our bash profile. So we can do ls-lah tilde/.bash profile. Now this tilde, that indicates our home directory. Does anybody not have a .bash profile? All right, sounds like everybody's got one. If you don't, you can create one with the nano command, and you can paste in everything here. So our bash profile, you can see if we wanted to make a change to our path, for example, to add a tool directly into our path, we could add it by modifying this path variable. So here we set path equal to itself, followed by a colon, followed by some other directory we want to add, followed by a colon, followed by some other directory we want to add. Now you may also notice that $home is another global variable. So we can echo $home, and it's going to show that the home variable is saved as our home directory. I do not recommend making modifications to your bash profile initially, but when we start to use tools like conda, you may consider adding that into your path. All right, now let's explore the LMOD system. So the LMOD system is a essentially toolkit where we can load software into our path. And then once it's in our path, we can use it. So this software is installed on the system, and we can see what's available with the module avail command. So if we type module avail, you'll see all the modules that are currently installed on the Sockeye system, and there are quite a few. Now, some modules, you can see there's quite a few here, will only become available to you when you load different software collections. For example, if you want to load CVMFSCC, this is a Compute Canada stack. There's also software collection from 2021 or from 2019. And you can also find more modules available to you when you load different GCC or General C compilers. But for simplicity and for now, we are just going to explore a few modules that are in this base Lmon stack called Git. So we will do module load followed by the name of a module / the module version. So we want to module load Git /2.31.1. So now if we echo our path, we can see that something has been added to it. In fact, a few different things have been added to it. When we loaded the Git module, you can see that we got a new directory here, Git 2.31.1 /bin. And so that directory is where the Git command is actually going to be sitting. And that's just been added to the front of all of the rest of our tools in our path. Any questions about the path? It's pretty complex, but it's useful in knowing when you type something into the command line, why you actually get something out. Now, if I was to remove, or we can type module list, you can see these are the list of all the modules that we have loaded. And if I type git -- help, you can see now I have access to the Git software. Oh, git -- help. Yeah, these are just, this is how you use the tool Git. Yeah. Okay, so if we type module list, we can see these are the modules that are currently installed. And if we want to get rid of that Git command, we can type module remove Git 2.31.1. Now, if I type git -- help, it doesn't know what the Git command is. So this path is important, and the module system is important in us figuring out how we can add software to the command line so we can use it. Yeah.
If you have multiple Git modules downloaded, you can just type in the Git without the help. Would it just publish priority does it take place?
Sorry, say that again. So if you have
multiple versions of Git
on
downloaded,
the system,
yeah, and then you just wrote like Git help, which one take priority?
yeah. So priority comes in order of your path. So it's going to start on the first part of your path in this directory, and it's going to look for Git. And if it finds it, that's the one it's going to take. So if you had installed Git executable, the Git into your /home/Richmond P/bin, then it would not use that one. It would take the first one it saw. You can also type, so if we do module load Git 2.31.1, we can type which Git, and you can see it's going to say essentially that matches to that, right? So which is a command, which if you said which ls, or I guess it's going to be the one in /user/bin/ls, right? Questions are great. We love questions. All right. Yeah.
One other thing, could you show the module available again, sort of the list of modules? Just one thing related, if there's multiple versions of Git or Python, something else in there. So I think MATLAB is a good example. In the middle, about halfway down, there's 3 different versions of MATLAB. If you only type module load MATLAB, then it's going to load the bottom one. So if you look at the brackets, you have bracket T, bracket T, bracket T, comma D. The D is for default. So that's the default module that gets loaded if there's multiple versions of the same thing. So if you don't specify the full name with the slash version, it'll load the one with the D. So, I mean, I can save you some typing, but also if you get a bit lazy with it, which I do, you may not load the one you want.
Right. So just to reiterate what the point Jeff was making is that there are multiple versions of MATLAB or of other tools. What's another? There's multiple versions of CMake. If you just say module load CMake, you're going to get the one that has this comma D, D meaning default in that space.
There's a way to customize it from the default.
No, I don't think so.
No, that's set by the system. So we kind of set it based on what would be the most commonly used, or say the preferred use. So if you need to load it for your own use and you have a specific version, just load the whole thing as skill. It's usually best practice anyway.
Yeah.
To do, say, the get/2.f.s. But just pointing it out in case you do the shortcut and find it all the right thing. It'll probably become more important as well for using singularity in future sessions, which we'll get into. And you can see there there's two different things.
Yeah. So the question just for the online crowd was about, can you set your default? And the answer is no, default is set by the system for you. And as we get into the later sessions, we will see the importance of actually typing out the full name of the module as opposed to just typing out the name of the module and leaving off the version. Cool. All right. Now let's explore some bash scripts with variables. See if there's any relevant questions. Okay. So we were exposed to the global variables, but what if we want to set a variable ourselves? Well, we can do that by giving the name of the variable that we want in our bash script, followed by the value of a variable. So this file, this variables and shell scripts, pwd. Oh, right. Yeah, my old cleanup job came through. RM-RF, very dangerous. All right, so now here, scripts. All right, so this script is, I believe, basic bash script with variables. Yep. Okay, so in this script, we can see at the top, we're setting a variable name. Here I'm calling it workshop dir, or dir for the workshop directory that we're using. And then I give the full file path to that workshop directory. I can list out that workshop directory by calling the variable with the $ in front of it. So here I set the variable, and then here I call the variable as essentially a input to the ls command. Yeah, so you set a variable, right? So I set this variable workshop dir equal to be this path. So now when I reference that variable with the $, it's the same as if it was $x, right? Dollar doesn't really matter what this is. It's going to go up to here. It's going to say, okay, workshop dir is equal to this path. So this ls is going to be equivalent to ls like that. Does that make sense?
Mm-hmm.
Now I'm also going to set a working directory or working dir, and I can change into that working dir, again, referencing that variable with the $. Now, these global variables, we can also access these in our bash scripts. Here, this one is echo $pwd. Anyone guess what that's going to do? Yeah, that is a variable that stores our current working directory. we saw the user already, and we can use that variable in our job scripts as well, and in our bash scripts. And lastly, you can make variables of variables. So here I set my workshop dir equal to some path, and then I reference this variable with a curly bracket and another curly bracket. So that means that I want to replace this with the value of $user, and then finish with core HPC basics. Any questions about variables? The value in variables is that when we get code that works, we can change the variables at the top of our code, and then it will work with different input or output files. You'll see why that's relevant in just a minute. So again, walking through this, we set or we declared our variable. We called the variable. We know that these are global variables, and we set this variable based on essentially a path plus another variable plus the rest of the path.
Is there a way to output a list of the variables you created?
Probably.
Remember that.
I know it isn't, but do you know what it is in Bash?
I think it's just get I think it saves your.
It's going to save them into some environment, but yeah, that's a question we will follow up on. All right, so let's go ahead and execute that. Now, the cool part about variables is that we can also just execute commands that have variables. So if you have set up your student space correctly, you should have this script. So this should be able to run this command. I have not set up my student space correctly. Oh, right, that's because this. Whoops. All right, so if you entered that in, again, like I said in the morning session, most of the command line is in interpreting errors. So I got this error. It says that there is no such file or directory. So I can ls/scratch tr precision health 1 because I'm positive that that directory exists. Richmond P core HPC basics, and I can see no, there is no actual basic bash script in this space. It is in scripts. There is my basic bash script.
When I pasted in that line, it says like $sign user. We must have changed, will that automatically switch it out with our name?
Yeah, so the value in using the $user is that when you put this in, that's going to be your CWL when you hit the command. When I type it, it's going to be my CWL. When Jeff types it, it's his CWL. And the value there is that this variable is letting us all work in our own space, but operating the same commands.
Sorry, consciously, I want to get it's print n, so print end, all one word, and that'll print all of the environmental variables you have saved. It'll be a bit of a mess because there's already a lot that are created by the system. So it can be a lot of kind of noise to scroll through. But if you have an idea of what you're looking for, you can always do print and space, and then something like user, and it'll show you the variable that's attached to, or the value that's attached to the user.
Yeah, so what Jeff just showed us is the printf command, which shows us all the variables that are loaded for our current session. Yep.
What exactly is the difference between calling the global variables with or without the curly braces?
So if the curly brackets, so the question is, what's the difference about using the curly brackets or not using them? So here, the variable is separated on both sides by a slash, which means that when it's separated on both sides by the slash, that will automatically dereference or get you out of the variable. Now, let's say the variable was something like if we wanted to make a variable based on another variable. So if I was to say, if I want to, for example, MySpace equals something like this. If I was to do $user underscore directory, it's going to see this as a single variable, right? So if I wanted instead to have it be Richmond P underscore directory, now it is, now it will replace this with the value.
But when you're executing script in the command line, you don't need the.
No, well, it would depend, right? So if I was executing the command line and I was referencing some user underscore directory, then I would need it. But because also here in the command line, it's flanked by these forward slashes, I don't need it. Does that make sense?
So you wouldn't actually need it in the last one.
You would not need it here, no. But it's best practice to use it when you can. Any other questions? Variables?
And when you execute the script, we're supposed to do the fill positions of the file.
If you execute the right script, I guess this is supposed to be with variables.
Sorry.
Yep.
The one that's in the lower box, that one does not need, sorry, if you go back to the slide. That one does not need the curly brackets, but the line above does, right? Because that's a variable within the variable. Or was that actually optional?
This is still optional. The reason why you don't need the curly brackets is because it's flanked by a slash. And a slash is not a viable variable character.
Oh, by having that.
Yeah.
knows that it has to.
Exactly.
Oh, okay.
So like I couldn't make a variable name. You couldn't make a variable name that was something like my/dir equals, right? That would be a not valid variable name.
So if your my workshop their variable actually ends with $user, like if you use that very last folder,
Mhm.
would that one need the curly or that one does not?
It would not need the curly.
Okay.
We'll experience some curly and some non-curly as we get into our code. Great question. So the questions really are about when we're referencing our variables, do you need a curly bracket or do you not need a curly bracket? And the answer is that you need a curly bracket if you're going to reference a variable that's followed by some other valid variable character, like an underscore, another letter, a number.
Like a fixed term.
Yeah, then it would think that this whole thing would be something like user underscore directory equals something. Does that make sense?
Sorry, yeah, I guess I now understood, like when you said that when you make variables within variables, I thought you were in the variable with the my workshop there,
Mhm.
not the user underscore directory. Like that.
Okay. Okay, well, it'll become more clear when we look at examples. Okay, so interacting with PBS Pro. So far we've just been working on the login nodes, and now we want to work on the compute nodes. So in session 1, we just stayed on the login nodes and we accessed the storage space and we accessed the data transfer nodes. But now we want to use the compute nodes. So a little bit about the sockeye file system. Your home directory, right, is a place where you can keep some small things like scripts. No big data should be kept there. The project directory, this is where we're going to keep the data that we want to store long term. And the Scratch directory, this is where we're going to actually run our jobs. Now, in the scope of this Precision Health Bootcamp, we are going to be doing all of our analysis and keeping all of our code on Scratch. but we will reference some larger databases and shared software on project. Now, when you process on the compute nodes, it's important to realize that the compute nodes can only write to the Scratch directory, meaning they cannot produce or write output data to project or to home. They can only write to Scratch. So if we think about the data flow on Sockeye, you're going to be interacting with code and data that you may store on your home or Scratch or project. But on the compute nodes, they are only going to be reading from these project directories, writing to the Scratch space, and then our final output we will copy back to the project space. So how do we, the compute nodes, how do we communicate with compute nodes? We do that via the scheduler. And so we're going to specify how many nodes we need, how many CPUs, how many GPUs, and how much memory. And we specify that with these parameters. So for example, the wall time we set with the parameter -L, wall time equals hours, minutes, seconds. So this is a wall time that will run for 3 hours flat, and then the job will finish or will die. The next is setting the number of nodes. So we will always run -L select. For this workshop, we're going to always keep this at 1. The number of CPUs. So here we'll use somewhere between 2 to 4. And the number and the amount of RAM. Here I'm asking for 16 gigabytes of RAM. We can also add parameters for the allocation code, which for this workshop we'll be using -A st strv1 -M ABE, which means that you will get an email when your job aborts, begins, or ends, and your actual email address. And I do encourage you, if you ever see my email address in one of your job scripts, please change it to be your own. Otherwise, my email will blow up.
So what is the PBS stand for?
What does PBS stand for? Portable Batch System? Yeah. Okay, so we're going to get, so these little parameters, these are not commands. These are going to be things that we are going to set in our commands in just a minute. So the node options that you can select from, we're either going to be choosing a whole node or part of a node. Now, we try to keep these resource requests accurate for what you need to do. Now, how do you know how accurate you were? Well, we're going to run some code and we're going to see how much we request and how well that reflects what we actually used while processing our job. Okay, so there's 2 ways to access the compute nodes. One is with an interactive job, where our command line is actually going to move onto the compute node, and the other is with the batch job script. So in this interactive job, we're going to submit it with Q sub. So here I'm running Q sub -I for interactive -lowercase l, and here I'm going to give the wall time, comma, I'm going to select a certain number of nodes, a certain number of CPUs on that node, and a certain amount of memory. The -Q, I'm going to send it to the interactive CPU queue, and -A, the allocation tag here is going to be STSTurvy1. So you can just copy this, and what that will do, if it works, it's always a big if, is that you can see we typed that in. Now it says Q sub, waiting for this job identifier to start. Now it tells me that the job identifier is ready. So the job is ready. And you'll notice that I have actually moved from being Richmond P at login 03. So I've moved from being on login, I'm on login 03. You might be on login 1 or 2. I've actually now moved. Now I'm over here on the compute node, which means I don't have access to the internet. So you can't run things like wget from this space. However, this is now a safe space. So if I wanted to try and run some code that from the command line, maybe I wanted to map reads to the genome on the command line, I could try those sorts of commands in this interactive space. So the interactive job is a great place to test code when you really want that quick feedback without having to put it in a job script. Does that make sense? Any questions about interactive jobs? Yes. So when we submit any job, whether it's an interactive job or a job script, we have to wait in the queue. And so the queue, I think that's our next bad boy, isn't it? Yes. So the queue we can see with QStat. So there are lots of people at UBC using the Sockeye server. How many people, Jeff? A few thousand?
Up there, there's probably around 700 right now.
After this workshop, there'll be 1,000 people using Sockeye. Now, all those people will have jobs they need to run. Now, if everyone was to run all of their jobs at once, the system would crash, right? So instead, we put a scheduler in place. And the scheduler says, okay, we are going to put these jobs into a queue, just like a line at Starbucks. And based on two things, your priority, whether you're a Starbucks Gold Star member or whether you were the first in line, will determine when your job gets accepted and run. Does that make sense? So even though this is just an interactive job, we still have to wait in the same queue. And we can look at the queue by typing QStat. And as you can see, lots of people across UBC, especially this person running thickness, that looks like a fun job, is there are lots of jobs running in the queue, right? Some of these are running, some of these are queued, meaning they're waiting to run, and then some of them will be E for error, right? Some of them will have quit with an error. So yeah, so if we type QStat, you can see there's only so many interactive CPU nodes, and maybe we've swallowed them all up by running these jobs. So if we do QStat-U $user, you can see my job is currently running. It's been running for 3 minutes. I've requested 3 hours. I'm taking up 16 gigabytes of memory. And this is something that I need to now exit. So if I am on this interactive compute node, I can get out of there with the exit command. So now you'll see that my job, which was there, is no longer going to be there. So if I do QStat, my job is no longer there. And if I do QStat-U $user, I no longer have an active job. So
I got it. So is that just?
yes,
the person in the meeting?
exactly. Just like the Starbucks line, someone got their coffee, moved on with life. Now you're up.
So yours is an interactive session. So if you close the terminal, you exit. Or,
Yes.
and then for people who are running things, do they have to keep it open or?
If you are running an interactive, so interactive is not a place where you should be doing a lot of processing, right? If you've got like a job that you think is going to run for a couple hours, you put that in a job script, you send it to the scheduler, it runs, and then it finishes, right? And so the interactive queue, the reason I show it is that it's good for testing things out and learning the command line and things like that. But as you can see, there's only so many nodes in the interactive queue. So if you have an active job, like if you are one of these people, if you hit exit, someone else's interactive job will now be able to get launched. and then they will be able to exit it. Any other questions about the queue? We all know why we have it. Right. There's only so many computers and there's more of us for now. So, yeah.
Is that command something you can run with? Whether you're in like the queue stat stuff, whether you're already in a session or outside of it?
Yeah, so you can run QStat on the compute node. And it'll still show you the queue. Okay. So we can see QStat. If you're one of these people, kill your job. If you're one of these people, what you can do, for example, let's just pick on someone, Habel. You can kill your job with QDel. So let's say I was to myself submit this job. And now I open up. Let's just show you this real quick. So we're going to look at the QDel command. So now, if I look at QStat, you can see I have a $u$user. I have a job that's in the queue. Now I'm going to be waiting for this job until all these other people free up the interactive CPU. Now let's say I decide I'm ready for lunch and I don't want to do the interactive queue. I can type QDel followed by the job number. And now, if I look at QStat, that's going to not be happy. Apparently deleted. Yeah. Now that job is no longer going to be in the queue. It's been canceled. So if you're one of these people, cancel your, you can exit. If you're one of these people and you don't want to wait, you can run QDel on your job identifier.
What happens if you find them on a job, but it comes up on, like, it reaches your, you set 3 hours?
Mhm.
Like, what would happen in that case?
If you set a wall time of 3 hours,
Say your job is in 4 hours.
it will die at 3 hours. Will be
And
killed.
So, like, could I go back and then run it for another hour until like,
No.
or would you have to start over?
Well,
Would you just have another one?
it would depend on the job. And really, if you talk about stopping and restarting, and it's a complex pipeline of jobs like map reads, convert them, call variants, that sort of thing, then you, if you have something like Nextflow or SnakeMake, you could figure out where you got to, start there, and then move forward. So if you get into pipelines, I recommend using a workflow manager. All right. Moving forward. So, any questions about interactive jobs? Cool. We're good. Let's keep on chugging. All right. So now let's go ahead and look at job scripts. So job scripts, we can take a look at our job script here.
Can you accidentally close another user's process?
No.
Okay. So it's restricted to just the ones you started.
Yes.
Oh, so-
Why is... Oh, because Sherlock, of course. All right, so if we look at this PBS Pro header template, again, we are just in our workshop directory, core HPC basic scripts. We can type cat PBS Pro header template. So this is the bare minimum you need to run a job on Sockeye. Now, the job that we're going to run is very simple. We're going to echo, hi, my CWL is $user. We're We're going to sleep for 30 seconds and then we'll put out the date. So if you want to receive an email, you can do this. We can copy this PBS Pro template header template. We can make it into PBS Pro header followed by your username. And then we can edit this PBS Pro header. We're going to add in here STSTRV1. Delete that. And then we're going to put in whatever your email is. We will save.
Yeah.
Aren't those comments or?
Yes, great question. So the question is, aren't these comments? Well, the difference is that this hashtag followed by PBS is we call this a directive for the PBS. So this is a PBS. This means if a line starts with one hashtag PBS, that means what follows is going to be a parameter for the job scheduler. So if there is a pound sign followed by something other than PBS, that is just a comment.
So it's been predefined on the system that the pound PBS is something same as the hashtag.
Yes.
Exclamation.
Yeah.
Something.
Yeah. So those are a different, those are a special case, right?
Okay.
So we could still use down here, we could have something like this is a comment, right? That's still going to be a comment. And even, at the sake of confusing you, if you did that, this is also a comment, right? It has to be just one pound sign followed by PBS.
So like if you took out the space between the hashtag and this, in the this is a comment, the lower one, that is still a comment then.
This is still a comment. Yes.
Sorry, going back, so you did CPU and you changing the
So you can either edit your template. I just copied the template into this, something with my name, right? So I know that that's going to be a job header that will work for all my jobs. And then we can Q sub it. So I can Q sub this one that I just made. Now, if you try to Q sub the basic template, you do not provide a valid allocation code and it will fail. So I will Q sub this job I just made. Now I will Q stat. And you can see I'm here waiting for my job to run. And then once it starts running, it's going to get an R. So you can see there's people here starting to run some jobs. There's some people still running interactive CPUs. If that's you, kill those. So if we type qstat-u$user, you can see this is my job. It's going to be running. All right, we'll give everyone a moment to look at their jobs. Mine has finished.
What's the usefulness of the sleeve?
It's not useful at all.
Oh, okay.
It just means sleep. That would just show you that like if there was nothing there, you might not see that your job ever was running.
Oh,
Right. So like if the command was just like ls echo, it would be done in like a millisecond,
Right.
and the scheduler would just be like run and
right.
so the sleep 30 is just there for you to see the job. All right, let's keep on chugging so we get some more interesting stuff. Yep. You would delete what's there and then type it in. Yeah, it's the file editor nano. When you're in that window, everything you type changes the actual file, and then Control O save, Control X exit.
Okay, guys, just get stopped.
So the product number, I let you use the keyboard shortcuts. For like the, that's what people like to control. Session.
Yes. Yes. Okay. All right. How we doing by a show of hands? Who's got jobs running, ready to go? Yeah. So if you put in your email, you should have gotten an email when the job started and when it ended. All right. So we're going to continue on. If you haven't gotten that job to run, don't worry. We can always come back to it. All right. Now we are going to get into a couple job scripts where we're actually going to do something meaningful other than just sleep for 30 seconds. So let's revisit our motivating data type. So we had FASTQ data, unmapped short DNA sequencing reads, and we want to map them back to the human reference genome. So what we're going to do is let's go ahead and change to this directory where we have been working. And if we ls./files, we can see there is a number of files in this directory. If we do a ls-l of files, we can see we've got a father R1 FASTQ, father R2 FASTQ, mother R1 FASTQ, mother R2 FASTQ, proband and proband, as well as gzipped and human readable for the proband. Now, these FASTQ files, we can take a look at, for example, proband r1.fastq. So if we look at more files, proband r1.fastq, we can see these are the actual DNA sequencing reads for an individual person, where we've got @ followed by the read name. Here, this is not much information. This is just telling us that it comes from a certain sequencing read archive, followed by the sequence of the read itself, followed by the plus sign, followed by the quality string. The other thing that we need in order to map the data back to the human genome, now that we know where our FASTQ data is, or our raw sequencing reads, we just looked at these, we need a human reference genome. Now this is going to be stored in this directory on the project space. So this is the first example of us using a database that I've already installed and indexed this genome so that you guys don't have to. So if we copy that command we can see that in this directory, there is the GRCH38 reference genome. This is the version that's used by the 1,000 Genomes Project. Those of you who like genomes have probably heard of the 1,000 Genomes Project. And it has about 3,000 genomes mapped against this reference genome. Now we can take a look at this FASTA file. And we can see that this file is essentially just, it starts with a greater than sign and then has the name of the chromosome and some information about that chromosome. So the first chromosome in the human genome is chromosome 1. And then if we hit spacebar, we can see this is the actual sequence of the human reference genome being printed to the screen. So we've got our FASTQ data. We've got our reference genome in FASTA format. Now we need to map it. And for that, we're going to use the bwa-mem command. Now, bwa-mem, if we were to type bwa-mem, the bwa command is not in our path. Now, if we want to use it, we're going to have to get it into our path. And I'll show you how to do that in just a second briefly. We're going to cover that in more detail tomorrow morning. So the bwa-mem command, breaking down what we need, and then I'll show you where this command is. It's bwa-mem, the reference indexed genome, which is going to be the FASTA file, and these alternate files .alt, .amb, .ann, BWT, I know that's a Burroughs-Wheeler transform, PAC, and SA. Now, I don't know what those index files mean, but I do know that this FASTA file has been indexed and it generated those output files. So we're going to type bwa-mem. We're going to point to that reference index, which we just are going to reference this file here. -T, we're going to give a number of threads. So if we're using 2 CPUs, we'll give 2 as our number of threads. -R, we're going to have some read group tag, which we won't get into much detail there. And then we have our FASTQ for read 1 and our FASTQ for read 2. So remember that when we first introduced these, the reads are paired. So for every R1, there is a corresponding R2. So the father has his first sequencing read, followed by the second sequencing read. Now, when I'm also going to show you commands, some of these commands we're going to run are going to get really long. And so in order to take a much longer command and to split it out over multiple lines, we use the \. So if I type bwa-mem followed by the index, I can then have a \, and then it's going to start the next line as if I was just building a long continuous line. This is going to be very helpful in cleaning up our scripts. After we get our aligned reads, those are going to be in a text format called a SAM file. Now, we want to convert those into a binary version called a BAM, and then we're going to sort that binary BAM by coordinate position, and then we are going to index that sorted BAM. So again, remembering that when I give angle brackets, we're going to replace these with actual values. So again, SAM tools is not a command that we have by default on the system. This is a command we have to get into our path. And we're going to do that with this handy little conda environment. Now, if you're interested in understanding conda environments, we will cover that tomorrow. For now, all you need to know is that these 2 lines in this script mean that we add conda to our path, and then we activate a specific environment called genome analysis that has the BWA and SAM tools in it. So just like module load, this command is going to put those directories that house these commands into our path so that we can use them. So at the top of this script, if we were to concatenate this script to the screen, at the top, we're going to have, again, there's my email, the account we're using. We're setting a maximum wall time of 10 hours, although this is not going to run for 10 hours. We give a certain number of CPUs and a certain number of gigabytes. Then I'm going to come down to here. This is the conda we just showed you. And then the next part is where I'm defining variables. So again, you'll see here that when we work with variables and we set these variables at the top of our script, setting them here, this is the place where we would make changes. So for example, if we had different input FASTQ data, we could make changes here. And then the code down here would never have to change. So again, here I am first going to run the BWA mem command. So BWA mem and then $genome index. So that's going to fill in this for the genome index. Then I'm going to give my FASTQ R1, which is going to fill in this. And so an example of building a variable that needs the brackets. Here, my sample is called proband, and my FASTQ file is saying it's in a directory and it's called sample_r1.fastq. So that's why I need these curly brackets. So what this will end up translating to is proband _r1.fastq. That makes sense? Clear as mud. All right. So we've set our variables at the top. Again, you don't have to make any changes. The only thing that you would change is the email at the top. Boom, with that big red arrow. So if you go into your files, into your scripts, you can what do we call this? Map and convert _ JobScript, map and convert _ JobScript.sh. I'm going to go here, make sure you change your email. Yep. More than one FASTQ file. What do you mean?
In your post. Like it says R1.
Where? Here?
Yeah. To get them a 172, but it all said _R1.
No. So first of all, the BWA mem command, right?
Yeah.
I'm passing it only one variable, right? Just as FASTQ R1. Now, if I set sample equal to proband and then I follow that with sample equal to mother, then the value of sample is going to be mother, right? As soon as you set, like if I was to come down here, I'm not saying you should do this, but if I was to do this equals mother, now it's going to look for mother _r1.fastq. Now, as far as processing over multiple files in a directory, that's part of the problem set for today that will show you how to do that. Yeah.
Sorry, when you said that you added the sample equals mother as a second line, does it overwrite the
Yes.
program? Okay,
Yes.
So only the mother.
Only the latest variable.
Okay.
So something to remember is that these are getting executed in order. So starting with CD PBS O worked here. That means change to the directory that we submitted from. Then we load conda. Then we set our variables. Then we run BWA mem with the variables we set. Then we run SAMTools view, sort, index, and flagstat.
The follow-up to that, if you wanted to run the program and the button, you have to like copy paste.
Yes. Yes and no. For now, yes. All right. Let's map some reads. All right, so we went through this. So looking at this string, if you're interested in this, this is just a read group tag. And a read group tag is just going to add essentially our sample name onto every read. Now, this is not something that you have to worry about. If you're interested in this, we can talk afterwards. So let's go ahead and submit this job with QSub.
That previous one, why the slash is all this? Like within the sample,
Oh, this?
yeah.
Oh, well, so that's a little more complicated. That's a \T. That's equivalent to a tab. That's a special character.
I see.
You guys ask all the hard questions. Love it. All right, so let's go ahead and submit this job because I know there's a lot of us and we might have to wait. So from here, QSub, map and convert scripts, map and convert job script .sh. Now, if we do a QStat, we can see lots of us have submitted. And they're starting to run. The fact that we are not waiting is good. Someone's job has already ended. So we can see that as we are running the job, we are creating this output SAM file. So one of the commands that I always run is ls-lahtr, which means list long all files human readable, sort by time in reverse. Now, why do I do that? Because whatever file is currently being created is going to be right above my command line. So we can see it finished the SAM file for a total of 52 megabytes. Then it was very quick about converting that to a BAM file, sorting that BAM file, indexing that BAM file, and then producing some outputs. List, long, all files, human readable, time sorted in reverse. It's the best list. All right, so why don't we start? So when your job finishes, you have successfully mapped reads against the human genome. Give yourself a pat on the back. Great job. So when every job runs, we're going to get a .e and a .o file. So this .e and .o, this stands for the standard error, and that stands for the standard out. So I can print those to the screen. So I'm first going to look at this error file. How do you check if your job is still running? Yeah, I'm asking you. Anybody want to help her? How do you check if your job is still running? QStat. All right, so here you can see that what was printed to the standard error is essentially what the job, what the software BWA was telling you it was doing. So first it read in the genome to memory. Then it started to read the sequences that we were giving it. And then it started to map those sequences. And it finished in real time, 60 seconds. Gone in 60 seconds. So now we can also look at our output. And the output, what was printed to standard out, was a SAMTools flagstat command. Now, what this showed us was that we mapped 122,000 reads in 60 seconds. That is bioinformatics at work. we can see how many of these reads mapped. 99.81% of our reads mapped to the reference genome. Very cool. We all mapped reads to the genome. We also got a SAM file. Let's go ahead and look at that SAM file. So if we look at more proband.sam, this SAM file is going to start with @SQ, followed by the contigs or chromosomes that were in our reference genome. Now, the reference genome we used has a lot of these unplaced decoy contigs. So we're just going to go ahead and scroll way down. I'm hitting spacebar here until we get to some reads. All right. Then it's going to show you the command that you ran. And then it's going to show you the reads. So every read, for example, is going to have a chromosome that it maps against, a position that it's mapping, and then some other information that if you're really interested, you can dig into. And if you're interested in this file format, I recommend you read all 23 pages of this format specification. But for the purposes of this workshop, what you really are interested in is that this read was mapped here on chromosome X. Now, we can also get info from our job that ran with qstat-xf. So I'll clear my screen. I can do qstat-xf on this job number. So if I hit enter, up at the top, the first thing that it's going to show me is the job name, the job owner, the CPU used as a percentage, the CPU time, the resources used, the number of CPUs I used, the amount of virtual memory I used, and the wall time. So here you can see CPU used, it ran in about 60 seconds. How much memory it used. So this is a lot of kilobytes. We can think that's megabytes. That's gigabytes. So I used 11 gigabytes of memory and I asked for 16. So that's a pretty good match between how much I used and then down here, how much I asked for. Now, if you ask for 16 and you use 1 gigabyte, you should modify your job script accordingly. So you're only using about as much resources as you need. In this example that I was running before, you could actually see in an earlier analysis, I only used 0.3 gigabytes, but I asked for 16. These new data files that we have, I was much more accurate in using what I asked for. Okay. Just before we move on, let's see where people are at. Looks like most of us finished our jobs. Nice. And then this guy came in, Okor and guy or girl. All right. So next, we're going to talk about how you can optimize your job performance for jobs that have, yes.
I don't know how much processor the power task.
How many CPUs? So the CPUs are going to be, I mean, it depends on your operation, right? If your operation can multi-thread, then it's worth asking for 1 CPU per data thread. Now, a tool like BWA, which is mapping reads against the genome, can give every single read a different thread. So it can map, if I was to run with 2 threads or 2 cores, it could map 2 reads at the same time against a reference genome. Now, some tools can't multi-thread. So giving it more CPUs doesn't actually improve your speed. But coming back to the read mapping, if I was to map 1 billion reads with 1 thread versus 1 billion reads with 2 threads, the 2-thread job would run about twice as fast. right? So it depends on your tool and whether or not it can make use of multiple data and core threads. Okay, so coming back, any other questions about jobs? Cool. So next, we're going to talk about optimizing job performance for jobs with lots of input output. Now this is using a variable called the temp directory or tempter. So every one of these computers on the compute nodes, if you're writing to project or to scratch, it has to go through a network filer to access the network file system. Each one of these nodes also has what's called local storage, meaning there is onboard disk that's right on the node itself. So if we were to map data like we just did, every single read is going to have to travel through the network to go to the scratch space. It's going to be much faster if we take every read and we just map it on the onboard compute node and then copy our final result out to the scratch space. An example of that can be seen here. So we can go ahead and print that out. Scripts, map and convert job script underscore tempter. Now, the only difference between these two jobs is that I'm copying the FASTQ files to the temporary directory. And then I change to that temporary directory. And now that I'm on the temporary directory, when I'm writing this output file, it's going to write to the temporary directory. Then I'm going to convert it into a BAM, index or sort it, index it, give some output, and then I'm going to copy only the final files, this sorted BAM and sorted BAM.bai, back to my final directory. Now, the value in doing this is that when we run things like in genomics, that SAM file we noticed was about 5 to 6 times as big as our BAM file. But if all we're interested in is a final sorted BAM, then these files that we create on the temporary space disappear when the job's finished. So it's good to make use of this $tempdir in your job script. Huh? At the top? Yeah. So a rough template for how it works using this temporary directory. Again, all of this is explained in much better detail in the sockeye documentation. In fact, why don't we go there? Uh-oh. All right, that's fine. So if you want to learn more about using the local scratch, you can do so by visiting the sockeye documentation using local scratch. So that's what that means. Local scratch just means it's, oh boy, it's on the compute node itself. So in general, what that means is that you're going to want to first copy your data over to the temporary directory, change to that temporary directory, execute the job until you get your final output, then copy that final output back to your final directory, which here, the final directory, I'm going to say is just on the scratch space. So if we want, we can do q sub scripts, map and convert, job script, tempter. And this is going to run the same exact job, except it's only going to return me a new version of the proband.bam and the proband.sorted.bam.bai. Now, it's important to recognize that these files that I have here, timestamped 1331 on July 25th, are going to get overwritten by the new job. Whenever it finishes. I think it's at about a minute. Oh, and it finished as I was checking. So now you can see, instead of writing out the SAM and the BAM files that I don't actually want, the only things that return to me are the sorted BAM and the BAI. And we can take a look at this error file. And we can see that we actually saw quite a dramatic improvement in speed. So the time was much quicker if we were to compare the job script with the temp directory to, let me just do tail dash n 3 star e dot star dot e star, something like that. Cool. So we can see that our first job ran in 60 seconds and our second job ran a lot quicker because it didn't have to copy or write that data over the network file system. So when you can, always try to write to the tempter. Okay, yes.
Is there like a limit of how much data you can put in?
Of course. So you'll notice that if you look here at the nodes, each node has 2 terabytes of onboard data. Now, if you're going to use a whole node, you get all 2 terabytes. If you're going to use only 2 CPU or 2 cores, 2 CPUs out of 32, you're not going to get access to all 2 terabytes. You're going to be sharing that 2 terabytes with everybody else working on that CPU node through the scheduler. So in general, if you're going to have a big data footprint, like if you're going to think you're going to write 500 or a full terabyte out, you're probably going to want to use the whole node so that you don't run into a clash.
So for the temperatures only, you don't need access to those intermediate files, if you don't want them.
No.
For example, because in some scripts I want to take a look at some intermediate files, then wouldn't be smart to put that into the temp field.
No. So intermediate files, if intermediate files are useful to you, you can still process on the temper directory and just copy them back out. Right. So in that example I showed, I don't need those files, so I didn't copy them out. But if I wanted to see the SAM and the BAM and then the sorted BAM, I could just copy all of them out. So it's always best to make use of the temporary directory, even if you don't need intermediate files, or if you need them. Okay, so that is it for the afternoon session. There are some things to do in the problem set for today, including if you look at the files directory, we have a mother and a father who could be mapped as well. In the scripts directory, I'm not going to go through this explicitly, but if you're excited about job arrays, here is an example job array where I'm running a job through essentially on indexes 0, 1, and 2. And then here, this is how I map all the reads in a directory. A little bit of fancy bash scripting. If you're interested in this, I can walk you through it, but it might be too advanced for an intro to HPC basics. But that is one way which you can run all of the files in a directory over the same chunk of code. So with that, we will take any other questions. I encourage you to try the problem set. And also I encourage you at the end of the problem set, there is a direction here about how to mount the file system. Now, the main reason to mount the file system is to use IGV. Now, I'm a genomics person. If you haven't figured that out yet, I love IGV. Now, IGV is something where we're going to visualize these BAM files. Now, BAM files are notorious for getting really big, like 50 gigabytes big. We don't want to transfer that to our local computer. So what mounting does is it allows us to essentially place this Scratch TR Precision Health 1 workshops directory onto our laptop. So we can access it and the files in it directly. And some instructions on how to do that, very simple on a Mac, on a PC. There's a great YouTube video. Watch that here, but I'm not a PC guy. So yeah. Here's some more instructions for mounting with SSHFS. With that, we will conclude the session. Thank you, everybody online. I'll keep the Zoom open, and hopefully that was useful to some of you.